Okay, so today we are going to start with your equation of continuity, as I told you. Okay, not difficult, it's easy. Equation of continuity will be easy. Bernoulli's theorem, I think you will understand, easy, not difficult, and Venturi Meter also, I think you will understand. Okay, so just check. Okay, I'll send you the notes after I'm done with the class. So check. Okay, what is equation of continuity? Okay, see, if you don't understand, please talk to me. You can tell me. Okay, see, let me remind you, we are still doing fluids. We are still talking about fluids, and the type of fluid that we are talking about right now is a non-viscous fluid. Non-viscous, no viscosity. This means the layers of the liquid are not going to apply force on each other and disturb the motion of each other. Okay, so we are talking about non-viscous fluid. Then one more is non-compressible. Non-compressible fluids. Okay, so these two types of fluids we are going to take into consideration. So non-compressible fluid also means that the density, right? I think you can understand. What do you think will happen, guys? If it is a non-compressible fluid, the density is going to change or remain constant?
Remain
constant, no? If imagine there is a fluid, okay, and you can compress it. If you compress anything, right, okay, what will happen to the density? Remains the same or increases? If you compress anything,
increases.
Density will increase, no? It will become very dense if you compress. Okay, so because I'm talking about non-compressible fluids, the density will remain constant. Okay, so what is equation of continuity? Okay, see, check. Suppose I have a pipe. Okay, we have a pipe from this is the one of the cross section of the pipe. You can already tell what is the property of this cross section, right? It is going to have certain area. Okay, so this has certain area. I can call it A1. Okay, that's the area of this cross section of this pipe, and this pipe can have different areas of cross section. Okay, that means it can become small also, big also. Okay, so I have this other end of this pipe which does not have a very big area but a very small area. Okay, let's call this area as A2. So we have another area here, we call it A2. In between I can also take other area of cross section, which is this one. I can call it A3 here. Okay, so this one A3. So this pipe has different area of cross section in different locations. I can talk like that, and let me tell you what is going to happen in this pipe now. Okay, see, the liquid that we are talking about, okay, is going to enter this pipe, let's say from this end, which is your cross section A1, and there is no source or sink. Let's be clear with that. Okay, no source and no sink in between the pipe. Okay, in between these two cross sections, between this and this, there is no source and no sink. That means no water can come from anywhere except the cross sectional area A1, and no water can leave from here. They can only leave from here. Okay, they can enter from A1. You can, I think I can make out, and they will enter from A1 and leave from A2. Okay, leave the water, whatever is going to enter from A1 will leave from A2. Okay, and there is no source and sink in between. That means no water can enter from anywhere else, and no water can leave also from anywhere else. Okay, so I hope you understand this part. Okay, then what happens is this, you see. Okay, the liquid which is entering right through cross sectional area A1, the velocity of the liquid, let's call it V1. Okay, that is the velocity. I hope you understand what am I talking about, right? Because liquid which is entering from cross sectional A1 will enter with certain velocity, right? So that velocity I'm taking it V1. I think this part is clear, right? I think all of you understand what is V1. Is it okay?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay, example, maybe the liquid is entering at the speed of 20 meter per second or 30 meter per second. No, that is what is happening in from this cross sectional area A1. Okay, and obviously you can also make out, I think. Okay, what will happen from the other end, guys? Liquid will come out or not? Yes, if it enters from there, it has to come out from there. So it will come out with a speed, let's say V2, and I think you can understand, right? It is going to be same speed or different speed? Different. Okay, different speed. Okay, let's compare V1 and V2. Okay, where do you think the water or the liquid, right, will come out faster? They'll enter faster or come out faster if the diagram is like this?
Come out faster.
Yes, come out faster. Okay, it doesn't mean that more water is coming out. Okay, no, Do you think more water is coming out or same amount of water will leave? Same amount of water. I'll give an example. Okay, if 10 liters of water enters here per second, how much will leave from here?
10 liters.
10 liters of water will again leave, has to leave per second. But because it's a very small area of cross section, okay, you must have done right in your home. Okay, you want the water to become very fast, no, out of that nozzle of the pipe. You squeeze the pipe, no, you make the area small. The rubber pipe I'm talking about, okay, not the steel pipe. Okay, you cannot do that, I know. Okay, so this speed here is going to be higher. V2 is going to be greater than V1. Even if I compare it this cross section, right, if I tell you the speed of water here is how much, let's say V3, no, then V1 will be greater than what? Sorry, wrong. V1 will be less than V3. That means speed of water here will be more than that, okay, and that will be much less than what? V2. The speed here will be the fastest. Okay, so what is equation of continuity? Let me quickly tell you that. Okay, you'll agree with me on that, check. Okay, equation of continuity is simply this. Okay, see, area A1 multiplied with velocity of the liquid at that area. Okay, V1 and A1. See, I'm multiplying these two. I'm multiplying the area here of cross section with the velocity of the liquid at that cross section. Okay, that is your A1 into V1. Okay, and here also I'll do the same thing. See, I'll multiply the velocity of the liquid at second area and also multiply with the area of the second area. I'm going to get here what? A2 V2. Okay, this is what is found to be equal. I'm not saying area is equal, no, that is wrong. I am not saying velocity is equal, that is wrong. But the product of what and what, guys? The product of area and velocity. The product of area and velocity is going to remain same, and that is true not only for this cross section, that is true for any other cross section I take. Okay, A3 V3. I can take another cross section where the area is A4 and the velocity is what? V4. This is found to be equal. They are not going to be different. Okay, so I think you understand what is equation of continuity, right? So tell me, guys, what is equation of continuity? Something remains constant. What remains constant or same throughout the flow of this liquid? Product of area and velocity. I hope you understand. Equal, right? So product of area and velocity. Okay, product of area and velocity remains constant. Okay, I hope you understand this. Okay, so we are going to use this. Not difficult, easy. Okay, we may use in some numericals also. Later I'll send you so we can easily use this. Okay, I think you are clear with this one. Is it okay, guys? This one?
Yes, sir.
Yes.
Yes, sir.
Okay.
Yes, sir.
Okay. Now don't forget what is our consideration. It is non-compressible, so density is constant. And we are taking streamlined flow. Okay, steady flow. What kind of flow of the liquid? Steady flow, not turbulent flow like that. No, some liquids. Okay, maybe later I can show you a video of turbulent flow and streamlined flow. I forgot to mention that. But we are also, of course, talking about steady flow right now. Okay, steady flow. Okay, now say, so I think we are ready to talk about this point now. Okay, check this one. Next thing what we are going to do is we are talking about Bernoulli's theorem next directly, actually. Okay, Arohi Paul. Who's Arohi Paul? Okay, the next thing that we are going to talk, is about your Bernoulli's theorem. And Bernoulli's theorem has to do with energy of a fluid, energy of any liquid. Okay, 1 second. Prayash, you did not come today? Hello, Prayash.
Yes, sir.
You did not come today? I was waiting for you. तुम्हारे लिए हम पिज़्ज़ा भी मंगा दिया था, तुम तो आया नहीं.
कल मंगाइए ना.
ओके, कल आएगा तो ठीक है, कल आएगा तो तुम लेके आना कल. हाँ, ओके, सही. अब पैसा भी चाहिए तुमको हम बुला भी रहा है कल. आज तो तुम मिस किए तो. ओके, सही. तुम आओ. तुमको वही ठीक करता है, क्या नाम था उसका, संभव ही तुमको ठीक करते हैं. तुम आओ खाली. ओके, सही. सो what are we doing here? Okay, see, Sambhav, not Sambhav, Prayas, see, okay, we are talking about total energy of a liquid or a fluid, but actually I can just call it liquid right now. Okay, because incompressible will be only liquid only, not gases. So let's say energy of a liquid. Okay, I want to talk about that using this diagram. Okay, maybe this will make many things clear. Okay, so see, The first thing is, look at the diagram. This is our reference level, this is our ground, and you know, right, the potential energy at anything which has no height at this level, right, this is the level, the potential energy is how much, guys, at this ground level?
0.
No height.
Zero.
Okay? No height. No height. No height means potential energy is 0. So at this level there is no energy, no potential energy. Okay, not talking about other energy, only potential energy. Okay, PE I'm calling it right now. Okay, let's look at the next part of the diagram. Okay, see, you can see here there is a container. Okay, you can see here there is a container. This is the container. Okay, in this container you can see there is a pipe going down, okay, from this container, and I fill this container with certain liquid. Okay, the level of the liquid is still here, till this much. Okay, I hope you understand till here. This is a liquid of certain density, the level is maintained here. I'll show you how. And liquid is obviously falling down from here, right? It's going down. I think you'll agree, right? Gravity will definitely make the liquid flow down. Agree with this, right, guys?
Yes, sir.
Yes, sir.
Just a container, and
Yes, sir.
there's a pipe going down. Okay, now if you check, there's another pipe here. This pipe, what do you think? Liquid is coming out of this pipe, or it is going into the pipe? Coming out, right? Yes or no?
Yes, sir.
Okay, so liquid is coming out, okay, from this pipe. Okay, and it is trying to go to this container, obviously, right? So some amount of liquid is entering. Okay, from here liquid is entering, and from here, what do you think? Liquid is leaving. Okay,
Leaving.
okay, if I tell you, okay, the same amount of liquid is entering and leaving, okay, what do you think? The height will be maintained or not maintained? The height, the level that we am talking about, this one, this level,
Maintained.
it will maintain, no, because whatever amount of liquid is entering, same amount of water liquid is I can say water also for the time being. Okay, no problem with that. Let me say water only. Okay, okay, I think you understand why the level is maintained there. Okay, so now I go to this cross section, one particular cross section of this pipe I'm going to go. Okay, this is the cross section. See, guys, x and y, this one. Can you understand me of cross section, guys? Jyotima is so sorry. Okay, others they can hear, but you cannot hear. That means I think your network problem, right? Others they can hear me. Okay, Jyotima. Hello, Jyotima. Hello, Jyotima. Hello, Jyotima. Others can hear. So you have to get an internet connection, the proper one, right? Other tuitions, the net was fine, he's saying. Hey, what to do now? He's blaming me now, okay? Now I am in danger. What to do? Other tuitions, you use what? Internet pack only? Jyotima, internet pack or broadband? Which one are you using? ज्योतिमय तो प्रॉब्लम है मोबाइल डेटा you have to get internet. See, maybe you have finished your net pack, no? Maybe. Okay, I do not know. Okay, I don't know what to say, but others can hear me properly. That means something is wrong with your soul, you know. Manba can hear me. Manba is writing yes. Yes means what? Manba can hear me properly. Okay. So okay, the Jyotima is so sorry. Okay, I don't know what to do. Okay, because I can't fix your problem. Okay, see, okay, guys, so we have this level that is maintained, and I told you I'm going to take one cross section of the pipe. No, this is the cross section I'm taking. Okay, basically what I mean to say, cross section is this area here, see, this part. From here liquid is going to flow, right? Okay, so I'm going to talk about now energy of the liquid exactly at this cross section. Okay, think and tell me. Okay, do you agree that liquid in this cross section, is it moving down? Yes, it's moving down. Is it moving with certain velocity? Yes, it has a velocity called v. So because it has certain velocity and it is moving down, right, do you agree that in this cross section the liquid will have certain called kinetic energy or not?
Yes, sir.
Okay, okay, formula for kinetic energy not different than any other, right? Formula is what? Half m v square. Okay, so let me just mark it properly. Okay, what is this, guys? I've written the first one of the first energy that I want to talk about. What is this, guys?
Kinetic
Energy of the liquid, okay, or water, okay, or fluid, okay. You will all agree with me. Liquids, they flow, they move, they have velocity, so they have kinetic energy, okay. So this is what I've written, okay. That's the kinetic energy there, okay. The next point is this, okay. This cross section, right? I think you'll agree with me again that this cross section has certain height from the ground or not. Check, guys. I've called that height as h1. You can see that. This one. This cross section has certain height with respect to the ground, okay. So you tell me, the liquid at this cross section has potential energy or not?
Yes, sir.
Okay. What will be the formula for potential energy? M
mg
into G into H, or H1 this time?
H1.
H1. Not in M into G into H, but it will be M into G into H1. Okay. I think this part is clear. All of you understood, I think, this part.
Yes, sir.
Okay.
Yes, sir.
Okay. This part till here is clear. Okay. Now you will also agree with me that the level of the liquid from this cross-sectional area, that means I'm talking about this level, okay, this level, we have liquids still there, and the height of this level, right, from that cross section, I have taken it to be h. I think you can see that, okay. Now let me ask you a question, okay. Say, do you agree that all these liquid molecules, okay, above this level, okay, above this level, that is your this level, okay, this cross section, okay, x, y, not x, y, but x, y, okay, all this liquid I'm talking about, okay, this one, say again, oops, cannot see it, but let me try this one. This liquid I'm talking about, all this liquid above the level x, y, okay, do you agree that they also have potential energy or not?
Yes, sir.
Okay.
Yes, sir.
They
Yes,
have
sir.
potential energy, okay. How much is the potential energy? Let me write again. Potential energy, okay, of this liquid here, this part, okay. What will be the formula? Now tell me. It will be M
mg
into G into H, or H1 this time?
H, sir.
H. They have potential energy, okay. And you will also agree with me that all this liquid above this level, right, okay, this one, all this liquid above this level called x, y, okay, tell me, are they pushing the liquid at this level or not? Are they applying pressure or not? That is what I'm asking you. All this liquid above this level called xy, okay, my question is, are they pushing the liquid here or not? What do you think? Pushing or not pushing?
Yes, sir.
Pushing.
Yes,
Okay.
Pushing.
So that energy, right, okay, that energy we have a different name, okay, we call it pressure energy. Can you understand? Okay, what energy we call it? Pressure energy. Okay, let's try to understand again, okay. Tell me, first part is very simple. The liquid here is moving or not? Yes, the liquid here is moving, so they have kinetic energy, quite all right, okay. The liquid here has certain height, that is h1, so it also has what energy, guys? Potential energy, M into G into h1, so that also is fine, okay. Now the another type of energy I was talking about is this, okay. I told you the liquid above this level xy, okay, the liquid above this level called xy cross section, all this liquid, right, tell me, they have certain energy, potential energy above, potential energy or not?
Yes, sir.
Yes, they have above that level, right? And what do they do with that potential energy? What do they do with all this liquid, right? What do they do with that potential energy? They apply pressure at this cross section. Can you understand? They apply pressure at this cross section, and instead of calling it potential energy, we call it what, guys?
Pressure.
Pressure energy, but the formula is different or same like potential energy? Same. Why? Because it is the potential energy only that appears here as what energy, guys? Pressure energy. Okay, so the formula is not different. That's why I wrote the formula. Look here. Kinetic energy is half mv square. Potential energy is m into g into h1 potential energy, and the pressure energy is how much? M into g into h. Okay. Now you have learned one more thing, right? If I have a liquid column, okay, up to a height of h, then how much is the pressure on the base? Provided I know the density of the liquid, no? Pressure. H rho g is the pressure here. I think you agree, right? Okay.
Yes.
So I just want to change a few things. Okay. So check. I want to write from this equation. I want to write I want to write H. Okay, I want to write what, guys? H. Okay, so what is H equals to from here? P divided by
Pressure
what?
by rho g.
P divided by rho g, right? So I'm going to use this. Okay, I'll show you where. Check. So we have our total energy, which is pressure energy, potential energy, and kinetic energy. In place of this H, I want to substitute by the actual value of pressure here. So P stands for the pressure at this cross section. Okay, and you can understand, right? More pressure means more energy we are talking about there. So that is what is going on right now. Okay, so we have that. So that is your P. Pressure at this point is P, given by H rho g, which is this one. I have written somewhere here. Okay, H rho g, and I'm going to use H in terms of P and rho and g. Okay, so that is what we are going to do. Okay, so yeah, this H I told you, right? I'm going to replace it. Tell me, what am I going to replace by? I forgot. You tell me. P is equal to H rho g. So H will be equal to P by rho g. Okay,
P by rho g.
P by rho and g. Okay, you can already see g and g what gets cancel, so don't worry, we have this one. Okay, so everything is sitting very nicely now. Okay, so I think now you know why I think I've done this one, right? Because it makes sense now, right? Because instead of talking about height above the norm, the level, the xy, now we're directly talking about what? Pressure at that level, no, from the liquids above it. Okay, so P we have directly. Okay, so now what we are going to do, let me show you. Okay, I'm going to use this equation. Let me just show you that. I'm going to use this equation, which stands for the total energy. Okay, and I'm going to write something called total energy per unit volume of this liquid. Let me just do that. Okay, so paste here, see. So this is what we have. Now I don't want to write total energy, I want to write total energy, what, guys? Per unit volume. Indirectly I'm telling you, it means that I want to find not the total energy here. Okay, not the total energy, but what? Total energy per unit volume. That is like writing total energy per liter. That means every liter of liquid. Okay, I'm repeating again, every liter of liquid, how much energy is present. Are you clear what I'm saying?
Yes, sir.
Okay, so I'm going to do that. Okay, so another name also is there, right? What can I call this one? Can I call it mass density, or can I call it energy density? We can call it energy density. Mass per unit volume is actually mass density. Okay, if I write charge per unit volume is what? Charge density. But if I write energy per unit volume is what? Energy density. That's how one way of using it. Okay, so now check. So I'm going to divide this whole equation by volume. Let's check. Okay, so half I have mass, I have divided by volume, capital V. I have this V also, don't forget this is the velocity V. Okay, so this is velocity square plus m by capital V again, which is volume. Okay, because I think you can understand I'm dividing entire left hand side by your volume, so I have to divide the entire right hand side also by volume. Okay, plus m by again your capital V, and we have P by density, which is rho. Okay, so now I think it's easy for you to understand what's going to happen next. Okay, let me just show you that. See, so the next thing that will happen here is this. See, total energy per unit volume or per liter of the liquid is equal to, what can I do with this, guys? Mass by volume. What can I write?
Half rho density.
Half density, then we have velocity square. Yes. Okay, plus this is also density, right?
G.
This is also density. So we have rho g and h1. H1 is the height of that level x, right, from the ground. Then we have again this one is also what? Mass into volume. Mass by volume is what again? Density. We have pressure again divided by density, so they will get cancelled. So we only are left out with what? Pressure. Okay, so now you tell me, what is this? What is this?
Total energy per unit.
Total energy per unit volume. Don't worry, I know till now not so much clear, but you understand, right? We are talking about total energy of a liquid. Okay, now it will be clear. Check. See, according to Bernoulli's theorem, look what Bernoulli is saying. Okay, he says this thing, the total of all this energy, the total of this, right? All this energy, according to Bernoulli, right? It is a what? It's a constant. It's conserved. That means what? Tell me. Can the potential energy change or not? Can the potential energy change of a liquid? Yes. Can the kinetic energy change? Yes. Can the pressure energy change?
Yes, sir.
Yes. Okay, but
sir.
what will not change? The sum of all of them, the total energy is not going to change. That is the meaning of your Bernoulli's theorem. Okay, now you're thinking, how come pressure energy is changing? You must be thinking, how come potential energy is changing? You must be thinking, how come velocity is changing? Okay, let me just show you an example. Okay, see, this is a pipe, okay, which is going down, okay, like that, no? And this is a liquid through here. Okay, think and tell me. Okay, this is a cross section called 1 and this is a cross section called 2, no? So this is the ground. Okay, now you think and tell me. Okay, where do you think we have more kinetic energy, at 1 or 2?
At 1.
At 1, right?
2.
At 1 or 2? 1, right? Because liquid as it goes down, right, because of gravity, right? Here will be slower or much faster?
Yes,
Much faster. Or I can just reduce the size of this cross section right now. Okay, let me do that so you can easily understand, right? Here we have a big cross section, here we have a Bobby Bora. Who's Bobby Bora? Okay, I think it is Jyotimoy only. Okay, Jyotimoy, no, I think, or who is this? Hello. Okay, so see, okay, so we have this cross section, no? We have this cross section here. Okay, I can just take it, let's say this is a smaller cross section. I can just tell you that it is smaller, forget about the height. Okay, smaller, this is bigger. So you can easily tell me now at least. Okay, tell me, where is the kinetic energy more, guys, in 1 or 2?
Sir, 1.
Okay,
1.
kinetic energy in 1, right, of this liquid is greater than kinetic energy in 2. Okay, I think it's Jyotimoy, no? Who's that? Jyotimoy only, no? Bobby Bora, I think it's Jyotimoy, right? Or who
Yes,
is that? Oh, yes, okay, fine. Now it's clear, Jyotimoy.
Yes, I tried to find out.
Okay, yes. Okay, now see. Okay, so this is a smaller cross section, means what? The liquid will be faster, so it will have more kinetic energy. Okay, but notice something. Okay, do you agree that if I compare, okay, 1 and 2, what is smaller here? Kinetic. Sorry. What is larger here? It number one. Kinetic energy is larger. Okay, but you will also agree, right? The potential energy here is larger or smaller? Here.
Smaller.
Potential energy is small. Okay, example. Okay, I'll give you a very bad example, but I think it will work. Okay, I don't think so. I have to do that. Okay, let's come back here. What do you think that happens to potential energy? Same or large?
Large.
Large.
Pressure energy I don't want to bring right now. Okay, just let's talk about kinetic and potential. Okay, it happens with pressure also, but let's understand this one. Say, you know what does it mean? If we have a region where the kinetic energy is what? Large. In that region, what can happen? The potential energy may be small. Okay, and in a region where we have potential energy what? High. What can happen in this region? The kinetic energy may be small. Okay, and you can bring the pressure energy and think like that. Okay, so do you realize if one of the energy goes up, the other energy will be down in one cross section, and same thing will happen in the other cross section. Okay, if one of the energy is low, the other energy will become what? High. As a result, the total here and the total here remains the what? Constant. I think you understand, right? Okay, it's like this. Okay, here you can understand easily. The potential energy, right, in this cross section has been converted into what energy? Kinetic energy, right? Okay, that's why the potential energy, as you go from here to here, the potential energy decreases, but it compensates that by increasing what energy, guys?
Kinetic energy.
And also the pressure energy. Not only that, but let's say also the pressure energy. Okay, so now we are going to prove all of this. See that the total energy is going to remain constant. No, we are going to prove that. Okay, the proof is here only, not difficult, very easy. This is the statement, you can read. Statement of Bernoulli's theorem is, for a steady flow of an incompressible and non-viscous fluid, the total energy density, that means energy per unit volume, always is going to remain constant throughout the flow of the liquid. Every time it's going to happen. Okay, that means this one, right? This is not the formula for energy. Okay, this is the formula for energy density. Okay, that is going to remain constant. Okay, so now we are going to prove it. Okay, for that I have this diagram. Okay, check whether it's making sense or not. Okay, so I'm going to speak slowly. Please check. Okay, the first thing is, this is the ground level. I think you are clear with this one. Just check, guys. Ground level is clear, no? Ground. Okay,
Yes, sir.
Okay. What is the potential energy at this level? You know, it is equal to
0.
Okay, fine. Everybody knows this one. No problem. Okay. All the height measurements we will make from this level. Okay. Now you can check. We have a pipe also. This is a pipe. And you know what? Initially the pipe is here. Let me just remove it. All these things. Not initially. This is the pipe. And you can make out. Okay, the pipe. What do you think? It has same cross section or different cross section? Different. Below it has a bigger one, but above it has smaller cross section. Below it has smaller cross above bigger, but above it has bigger. Okay, so what am I trying to do here? Let me show you. Okay, in this pipe, this cross sectional area here, okay, this one here, I am saying the area is A1. Is it okay, guys? How much is the area? How much is the area? A1. Okay. This here is the piston. Can you understand the piston, right? You know what is piston, no? Just like an injection, right? Okay, this is a piston here. Okay, this is a piston there. So not a problem. You can understand this. Okay, if you notice, we have another piston here. Okay, that is called piston 2. This piston 2 is located in a smaller area, and the smaller area I have taken how much? A2. Can you see that? This is the smaller area. See. Okay. So the pipe has smaller area there, and the pipe has a bigger area here. Okay, and what is in between these two pistons? Let me tell you. Okay, in between the two pistons, I am filling it with a liquid. See, this is the liquid here, totally filled. Between these two pistons, we have a liquid totally filled. I think you understand the diagram.
Yes, sir.
Yes.
Okay, this part is clear. Okay, fine. Now I'll tell you what is going to happen. Okay, I'm going to push the piston. Again, I'll repeat. I'm going to push the piston number 1, and I'll do that by applying how much force? F1. Okay, so I'm going to apply that force over here, and you'll agree with me, right? The piston will be there, or it will move ahead. Move ahead. So 1 dash. Okay, the location now of the piston is 1 dash. Okay, so now you think and tell me. Okay, if the piston has reached from here to here, do you agree with me that all this liquid here will remain there, or it will be displaced?
Displaced, sir.
It will not be there anymore. Okay, so the piston itself has gone from here to here, no? So the liquid, no, will move, okay, ahead. Okay, ahead. It will be displaced. Okay, the displacement from 1 to 1 dash, I have taken it to be delta x1. Are you clear what is delta x1?
Yes.
That represents the displacement of the piston 1. Okay. Okay, so when I push it, right, do you agree that the velocity of the liquid here will be how much? Can I call it v1?
Yes, sir.
Moving, no? Liquid is moving, so they have some velocity, right? Let's call it how much? v1. Velocity, huh?
V1.
Velocity. Okay, I think this part is clear till now. Okay, now check. Let's look at 2. What will happen? What do you think? This piston 2 will still be here, or move forward, or move to the right?
Move forward.
Move to the
Right. Okay, but I think you'll agree, right? By looking at that picture already, right, you can see, right, the force on this piston will be from the right side or the left side. Means it will act towards the left or right?
Towards the right.
Towards the right. The force, no, the piston will move to the right. But what do you think? This piston has a tendency of going to the left or the right. Without any force, it has a tendency to go to left or right?
Left.
To the left. Can you understand? Without any force, I'm repeating again. Without any force, the piston has a tendency of going to the left or right?
So to the left.
Because of gravity, right? This piston wants to fall down, right? Because the liquid wants to fall down. Don't think I've kept a piston there doesn't mean that it will just stick there, no? So the piston has a tendency to go to left. Okay, so you tell me, what will happen? Will the piston 2 remain there, or it will go to new position to the right?
It will go to a new position.
To the right. Okay, provided what should happen? The force should be good enough, right? The force F1 should be what? Enough to send the piston 2, right, to the right. Are you clear? Little bit of force, okay, little bit of force, this one. Little bit of force may not push the entire thing to the right. Can you understand my point? I think you understand what I said just now. So this force, right, has to be good enough, right? This force has to be good enough to push and oppose this force, okay, this to push and oppose this force, so that the piston is really going to move to the right. Okay, I think you agree with that, right? Check.
Yes, sir.
Okay, so now you
Yes.
tell me, will the piston be at 2 or new position called 2 dash?
2 dash.
2 dash. So whatever the volume was here, please check, okay, whatever the volume of liquid was here, right, all this volume of the liquid, right, okay, will be now displaced, and the piston 2 will reach, okay, a new position called 2 dash, and it the liquid that will displace, right, occupies so much space there. Can you see? Now you tell me, this is the location of the liquid that has been displaced. Do you agree that the volume there and the volume here will be same or different?
Same.
Same. If I displace 1 liter of water here, how many liter of water will be displaced here?
1 liter.
1 liter. Okay, so the volume is going to be same. Okay, but what do you think? The displacement of this piston, right, 2, is it same or it will be much more? The displacement
Much more.
much more, because it's a smaller area, right? To compensate for the entire volume, right, the length should be very large or not? I think you agree with this, right, guys?
Yes, sir.
Okay, so now tell me this time, okay, the liquid will move to the right or
Yes,
not?
sir.
The liquid will move where, guys? To the right. But what do you think, same velocity or higher velocity? You can easily tell me that.
Higher velocity.
Higher velocity, yes, okay, because it's to cover so much distance in same time. Okay, I think this part is clear. All of you understood this part, right? Okay, I want to bring this one now. Okay, check. Okay, let me use green. This level of this first cross section 1, okay, is how much we are taking, how much height? H1.
H1.
Okay, and the level of this, okay, what do you think? I'm going to take how much?
H2.
H2. Okay, so now I'm going to compare number 1 and number 2. Okay, tell me, is there a pressure acting at 1 or not? Pressure at 1. Here.
Yes, sir.
Okay, how much is the pressure? P1, let's call it, no? And how much is the pressure this side? P1 or P2 we'll call it? P2. How much will be that? Force per unit area. Here also how much will be that? Force per unit
Force per
area.
unit area.
Okay, so we have both of them. Okay, force per unit area, force per unit area. Okay, fine, we got pressure. Okay, I think you'll also agree. Okay, do you agree that we are doing work on the system or not? Are we doing work on this system? Are we applying force and producing displacement or not?
Yes, sir.
Okay,
Yes, sir.
okay, fine. You will also agree with me that I have shifted some of the liquid, right, above. Okay, so I've shifted some of the liquid above the normal level, right? I'm shifting the liquid from a height of H1 to which height?
H2.
H2. Okay, so I think you'll agree with me, right, that do we have the same potential energy, or we have changed the potential energy of the liquid that has been displaced?
Changed.
I shifted. Okay, I pushed the liquid from down, it has gone up, so I have changed the height of the liquid. So I have changed the height, that means I have changed the potential energy of the liquid. Okay, and you can also see we have also pushed it in such a way that the velocity also, right, changes in those two levels. Okay, so no problem. We are almost ready to proceed. Okay, the first one is very simple. I'll tell you what is that. This is, I'm going to write here. See, what is this, guys? A1 into delta x1. What is this? This is what? Volume, right? Area into distance, right? This is volume or not? Check. The area here is how much? A1, and this is what? Delta x. So this A1 into delta x represents what? The volume of the
Volume.
liquid between 1 and 1 dash. I think we agree with that, right?
Yes, sir.
A1 into delta x1 is nothing but what, guys? Volume of the liquid between what and what? Between 1 and
1 and 1 dash.
1 dash. Okay,
One
here
and one
here
dash.
what is the volume, guys? Tell me, what's the area here? A2 and into delta
Plus.
x2, no? So yeah, this is what? This is nothing but
Gondo.
Sangam, we can hear you. You're eating something?
Sorry, sir.
Okay, Sangam, check. Okay, I was saying something there. What was I saying? The volume here is how much? A1 into delta x2. Already I know it has become so much. Okay, but you agreed to me, right, that the volume are different or same? The volumes are same. Okay, and you know the formula for volume is what? Mass by Density. Density is volume
Mass
by
by
mass by volume. So volume is mass by density. Okay. So this part I don't think so you have any problem. Till here is clear, right? This part. Check. Starting very easy.
Yes, sir.
Okay. So
Yes, sir.
next thing I'll calculate
sir.
the work done. Okay. Next thing I'll calculate what? Work done. Let me ask you. Okay. How much work do you think I'm doing? The formula for work done is what? Force into displacement. So I'm going to write F1 into delta x1. I'll write F2 into what? Delta x2. This is one of the work done. This is also work done, right? But these two work done, what do you think? They are in the same or opposite direction?
Direction.
Opposite. Same. No. When I apply the force from this side, right, the liquid goes up, and on the liquid there's already a force acting in this direction, right? That is how much?
Oh, yes, sir.
F2, right? This F2 doesn't want the piston to go up. Okay, so what do you think? The piston wants to go down, right? Because of what? Because of F2, right? The piston wants to go down. But because we have applied a force here, right? So we have done work against this force also or not? What do you think?
Yes, sir.
Okay. So how much work is done by us? F1 into
Delta x1.
x1. But this force, right? This work done has to be removed by what? Work done by the force which is already there. That is what? F2 delta x2. Can you understand this one? Can you understand what is happening? The work done from our side is this one, right? And the work done which is already there, right, from this side, which is where there's a force here on this side, no? He is also doing work. How much? F2 into delta x2. That's the work he can do, okay? But since they are oppositely directed, right, so there has to be a plus or minus. Should I add or subtract? What do you think?
Subtract.
Right.
Subtract. Okay, so what does this represent, guys? This represents work or total work done?
Total work done.
Total work done.
Work done.
Is it making sense? Just check, guys. Is it making
Yes,
sense? All of you are quiet right now. Some of you are quiet, okay?
Yes, sir.
Okay, Rajdeep.
Yes, sir.
Rajdeep. Okay,
Yes,
Deflin
sir.
also is there. Provina is
Yes,
also
sir.
there. Then who else? Others? Okay. Ronika. Priya is also there. Okay. So see, okay. Parthiv is also there. Okay, now see. So I was saying something, okay. So yeah, I was calculating the work done, okay. So I just want to arrange it a bit more. In place of force and displacement, check what can I do. Let me just show you here what am I doing, okay. In place of force, what can I write, guys? Pressure into area. That's not a problem, you can do that. And just now I'll go, right, A1 x1 A2 x2, right, it is m by rho. So I'm just going to use that now, say, because now we have area, no, and this one side, in place of this I'm writing mass by density. Here also I'm writing what, guys? Mass by density. So I'm simply going to get P1 minus what? P2 m by rho. So what have I calculated, guys?
Work done.
Work done, right? We have calculated work done on the liquid, okay. So, and that is like a P1 minus P2 m by rho. Okay, so we have just done that, and I think you will agree with me, right, that there is a theorem, okay, which is called work energy theorem. Now whenever we do work on a system, it should be equal to the amount of change in energy of the system or not. Example,
Yes, sir.
I take a box, I spend energy on this, I do work on that. When I do work on this, right, okay, tell me what happens to me. I lose energy or gain energy?
Lose energy.
When I do work on this object, right, I lose energy, but the object what?
Gains energy.
Gains energy. That means there's a change of energy, right? Example I can give you, if I've done 10 joules of work, if I have done 10 joules of work, I have lost how many joules of energy?
10 joules.
10 joules. That means this object must have gained that energy or not?
10 joules.
Yeah, 10 joules. I lose 10, the object gains 10, okay. Same thing goes here also. Just now we calculated work done on the liquid. Do you agree with me that the work done on the liquid is nothing but equal to the energy gained by the liquid or not?
Yes, sir.
Okay, so look at this. The work done on the liquid must be equal to change in potential energy of the liquid and change in what? Kinetic energy of the liquid. And that is easy to understand because you can understand, right, okay, that there's a change of height or not. Because
Yes, sir.
we have done work, okay,
Yes, sir.
because we have done work, we have changed the height, so that means we have changed the potential energy, and of course we have also changed the velocity of the liquid or not. So that means there's a change of kinetic energy. Okay, I think this part is clear, right?
Yes, sir.
Okay. So yes.
Sir, can
Yes,
you
sir.
repeat, sir?
Yes, I can repeat. Okay. Just now I told you, if we are going to do some work, okay, what does it do when we do work on any object? Will it make the energy of the object constant, or it will change the energy of the object?
Change, sir.
Change. Okay. Here also, do you agree that we have done work or not on the liquid?
Yes, sir.
Because we applied force and produced what? Displacement. Yes or no? Okay.
Yes, sir.
So we have done work on the liquid. Okay. So you can also check when we did that, right? The liquid from here has risen. Has rised. Okay, whatever it is. Okay, rise. No, the liquid has rised from its normal height or not? Whatever volume we
Yes.
have pushed, right? So do you
Yes,
think
sir.
there is a change of potential energy or no change of potential energy?
I don't think so, sir. Or is there?
Gaining height. Imagine,
Oh, yes, sir.
imagine,
Change, sir. Yes, sir.
imagine I pick you and put you on a building. That means I've done work, no?
Yes, sir.
And you have gained what energy?
Potential energy, sir.
So this liquid also gained or not, or change or not?
Yes, sir.
It already had, okay, potential energy. It already had. At what height it had already energy? H1, no? Now the liquid which is going up there now has a height called what?
H2.
H2. So it has definitely changed the potential energy. So what is the change in potential energy? Let me write it down. Say, do you agree with this one? Check.
Yes, sir.
What is this? M G into what? H2 minus M
G
into G into
H1.
H1. What is this? Potential energy or
H2.
change of potential energy?
Change, sir.
Change of potential energy. Okay. Similarly for kinetic energy, do you understand, guys? This is the change in kinetic energy or not?
Yes, sir.
Okay. And I think we can understand, right? They are not same velocities there. Okay. So this is the change in kinetic energy. That's the change in potential energy. Must be equal to what, guys? What we have learned? Must be equal to
Both, sir.
work done. Okay. And work done, we have already shown you this much, right, guys? Check this one. Okay. Do you remember? We have got this one, no?
Yes, sir.
Okay. So now we are simply going to arrange. Okay, guys. If you look from both sides, what is common in both sides? You know, M is common, right? Check. M. So cancel. Okay. Then if you remember this, there's a density here. This density is here on the right hand side. Can I take this density on the left hand side or not, guys? Cross multiply, right?
Yes, sir.
Okay. So how is it going to look like? The first term, check. It will be half mv square or half rho v square?
Half rho v.
Half rho v square. Okay. Just check one by one. Okay. Then the second term will be what? Minus half rho v1 square. This term here, okay, the mgh term, okay, will become how much? Rho gh2. This will become rho gh1. Okay. And finally we only have here what? P1 minus P2. Okay. Now we simply need to arrange. That's it. Okay. Check. I'm going to take the P1, keep it on the right hand side. So that is P1, which is plus and plus same. Okay. This is also plus here. This is also plus. I'm going to take the 1 1, all the 1 1. Okay. This is also 1. Check. This is minus. Okay. This is also minus 1. I'm going to take it on the right hand side. Okay. So I'm going to get this one and this one. Check. Don't forget, this is your kinetic energy per unit volume. What is this? Potential energy per unit volume. And what is this, guys? And what is this? Pressure or pressure energy? Pressure energy per unit volume. Okay. And automatically, right, I'm going to shift all this on the left hand side.
Sir, it will be rho gh1.
Rho gh1. Oh yes, very good, very good, very good. You have eyes. Okay, very nice. Okay, so this will be rho g h1. Okay, he has very good eyes. Not only eyes, but he has very good eyes. Okay, so yeah, please check the mistake. Okay, so are you clear with this one, guys? Check the one I'm just transferring in the right hand side. Okay, so all the two will be on the left hand side. They will all be plus. You can check that. That's not a problem. Okay, so right now I think I can say that we have proved it or not. Check, guys. Did you answer? We have proved it, guys. What is this?
Yes, sir.
Pressure energy per unit volume, cross section 1. Potential energy per unit volume in cross section 1. Kinetic energy per unit volume in cross section 1. Pressure energy in cross section 2. Potential energy in cross section 2. Kinetic energy per unit volume in cross section 2. Do you agree that the sum of all of this in the cross section 2 is same as the sum of all of this in cross section 1 or not? They're equal or not equal?
Yes, sir.
Equal.
That means the total will be different or total will remain same.
Remain constant.
And that is your Bernoulli theorem, right? Yes or no? I think you understood, right?
Yes, sir.
Yes, sir.
You have
Yes,
to go
sir.
through. You have to go through. Okay, you have no other way out. Okay, here.
Yes, sir.
Yes. Okay, you have to go through once. I do not know exactly. Okay, whether you have really understood or not, but the derivation has to be done like this. Okay, the proof is like that. You check once the steps. I think I have told you almost everything about this right now. Okay, so what is the application of this? Let me just show you that. Say, okay, guys. Say, see, if I have a pipe. Okay, I take a pipe which looks like that. Okay, and here sorry Jyotimay, what to do, you have been missing, no, because of your network. Okay, I'll do like this. I'll save this video, you can watch later, Jyotimay. Okay, I do not know right now what to say to you, no, because see, your network you have to fix, no. Okay, Jyotimay, hello Jyotimay, can you hear me? Okay, can you do in Zoom? No, Jyotimay, Zoom is not possible for me. There's some problem with Zoom, right? Jyotimay, you change your network, you do something, you take broadband or something, you have to take, right? Okay, check. Okay, see, then I was saying something, right? Yeah, so what am I trying to do here? Okay, my diagram is bad, let me remove my diagram. What am I drawing? Okay, see, I have a pipe here, I have an opening here. Okay, the same pipe goes and becomes narrow here. I have opening here also. I'll explain to you what is the meaning of this opening here. Let me draw it properly. Okay, there's an opening here, I have an opening here as well in this narrower pipe. Okay, then it goes and becomes broader again. Okay, notice something, see, this is the ground and this is a horizontal pipe. Okay, in a horizontal pipe, okay, let me ask you, what do you think is the level of, this is cross section 1, let's call it cross section 1, let's call it cross section 2, let's call it cross section 3. Okay, we have 3 cross sections. No, this is a bigger one, this is a smaller one, number 2 is a smaller cross section, this is again same like your number 1. Okay, let's say the liquid here, is again going from left towards right. Okay, this is how the liquid is flowing. Okay, this is how the liquid is flowing. Okay, through all the cross sections there it is moving. Okay, since there's an opening here, okay, you can understand, since there's an opening here, the liquid will rise up, right? Yes or no? To certain level, right? Do you understand what I'm saying, guys?
Yes, sir.
Okay, there's an opening here, no, like that, say. So the liquid from there, right, whichever is here will also rise here. Okay, let me tell you to what levels they are going to rise. Okay, so please check. Say, first of all, because it's a horizontal pipe, let me ask you, okay, what about potential energy here, potential energy here, and potential energy here? What do you think? They're different or same?
Different.
They are at averagely different height or same height?
Same, sir.
Same height.
Same height.
All these 3 cross sections, they have same height. That means the potential energy here, the potential energy there, and the potential energy there, right, will be different or same?
Same, sir.
Same potential energy. Okay, good. Okay, so now I'm going to write the formula again. Okay, please let me just copy and paste the formula. Okay, then I'm going to use it. Where is the formula? This one. Okay, it already looks so bad, right? Okay, this one. Okay, oops. Okay, see, let me put it somewhere here. Okay, so tell me what is same in cross section 1, 2 and 3? Potential energy. That means this one, right? This one and this one are H G also, right? This one, right, are different or same, guys? Check. Same, no?
Same.
In cross section 1 also and cross section same. Okay, so I'm only left out with what? A formula which looks like this: rho half rho V2 square plus P2 equals to half rho V1 square plus P1. Okay, so I'm talking about only pressure energy. Okay, this is the pressure energy. You can see This is also the pressure energy in cross section number 2. Now I am going to ask you a question, okay? So be ready. That's why I have drawn all of it. I do not know whether you are understanding or not. I do not know whether I'm talking properly or not, okay? Please check, okay? See, do you agree that in the second cross section, okay, the speed of the water is same or faster compared to 1?
Faster.
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 So V2 is greater than what?
V1.
V1.
V.
Okay. If V2 is greater, right, then V1 and this one is smaller, right? Kinetic energy will be less. Okay. What will you conclude? Because it has to be equal, right? Sum of these two will be equal, right? So where is pressure more and where is pressure less? Please tell me that.
So pressure is more in P1. Is
P2.
Pressure in 1 will be more because there what energy is less? Here the kinetic energy is less.
Less.
Okay, and pressure in P2 will be what? Less, second
Less.
cross section, because there already kinetic energy is what?
It's more.
Okay, pressure is like pushing power, okay? So pressure is like pushing power, no? So what do you think will happen here? All these liquid molecules in 1, okay, I'm repeating again, in 1 will have pressure or more pressure?
More pressure.
So they can really push, okay, the air molecules up and up. Do you understand? They are going against gravity. Can you see that? So the height here, the level, right, of the liquid inside this tube, no, is going to be very high, showing you more pressure. Can you understand?
yes, sir.
If the liquid there, no, goes up and up against gravity, it is going, no. So what does it mean? They are pushing the air molecules there, right? Because they have more what? Pressure, but they have less what energy?
Kinetic energy.
Less kinetic energy here, okay, in this tube, but they have more pressure, okay. They can push any air, okay. Even if I would have drawn down here, no, what will happen? Tell me. The liquid will be able to push or push more here.
Push more.
Push more from any side. Any side you just open it, no, they will have more pressure, okay. What about here, guys? What do you think? The level will be very high or very less here inside this tube?
So less.
Less, because here you can also understand, because here the liquid, no, the liquid molecules are moving so fast towards the right, they don't get a chance much, okay, to push the air molecules here. Can you understand? So here the pressure will be what? Low. Okay, you can just do this by simply doing this, okay. Check, you take out your hand, okay, this is your hand, very bad diagram, I know, okay. You put it flat horizontally, okay, and you know what, you blow air, all this air, no, they are trying to hit your hands, right now. If I just take out my hand, no, all these air molecules will come and collide with my hands or not?
Yes, sir.
Just
Yes, sir.
take out your hands in the open, right? The air molecules will come and hit your hands. But if I start blowing air, all these air molecules can go to the right or not?
Yes, sir.
Okay, now what do you think? My hands will feel pressure or less pressure?
Less
Less
pressure.
pressure.
Why? Because the molecules are not hitting my hands now anymore, no? Because they are just going away from my hands now, because I'm blowing them. Can you understand?
Yes, sir.
Okay, because I'm really pushing them so much. So now, so I'm really pushing them so much that now the air molecules are not getting chance to hit my hand or apply any pressure on my hands, because they are moving with high velocity. They are going to the right, so they don't get a chance to push my hand, okay. So as a result, the pressure on my hand is what? Less now. I hope you understand this one, right? Did it make sense?
Yes, sir.
Okay, I'll show you something more now, okay. Check, I'll show you something more, okay. Have you seen aeroplane wings?
Yes.
I'm not drawing them properly, okay. They are designed in such a way, you know, when the aeroplane moves forward, no, on the top, okay, on the top of the wings, okay, you have higher velocity of the liquid, or not liquid this time, but air, okay. Somewhat we are applying to air also right now, okay, whatever we have learned just now, okay. So think, okay, so if the air, right, is the design of the wings is such that air on top of it will be moving faster, okay, and the air below it moves what? Faster or slower? Slower, okay. So now you tell me, air molecules from top, they'll push the wings up or down? They'll apply pressure up or down?
Down.
Down, and the air molecules below the wings, okay, they will try to push the aeroplane up or down.
Up.
Up, right? These molecules, okay, the below molecules, right, which I'm drawing right now, can they push the aeroplane down? No, they cannot push the aeroplane down, right? They're already below, right?
Yes.
Okay.
Yes, sir.
So here the aeroplanes will be what? Pushed from this side, they will be pushed up, and from here they will be pushed where? Pushed down.
Yeah.
Okay, now you think and tell me. Okay, as I told you just now, how are they designed, guys? Here the air molecules, they move faster, and here the air molecules, they move
Slow.
slower. Okay, so now tell me, P1 and P2, which pressure do you think is large?
P1.
P2. P2.
Here kinetic energy in the one, right? Kinetic energy is same or high?
So high.
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 So here the pressure energy will be what?
Lower.
Lower. Okay, and here the kinetic energy what? High or low?
Low.
Low. So here the
Low.
pressure energy will be high or low? Higher, no?
Higher.
Higher. So now do you understand why the aeroplane will go up? Why does the
Yes, sir.
aeroplane goes up? It's because of low pressure created in the upper half, right? And high pressure is created by what? In the lower half. Can you understand? This is again because of Bernoulli's theorem or not? So this is because of which theorem? Bernoulli's theorem. If a region has high kinetic energy, then that region will have what? Low
Low pressure.
pressure energy. Okay, and if the if a region has low kinetic energy, then it will have
High pressure.
high pressure energy. Okay, so that's why the okay, this is called aerofoil lift also. Have you heard about this? Aerofoil lift, no? Okay, I'll send you the note, you can just read out with. Okay, guys, at this point I really want to ask you, okay, did you really understand? Do you really understand what I'm doing?
Yes, sir.
Ishita understood, Abhijit
Yes, sir.
understood, Rajdeep, Soumitra,
Yes,
sir.
sir.
Dexway understood. Daphne is not speaking. Daphne is getting angry. Aisha is not speaking. Asha understood. Okay. Parthiv understood. Ronika understood. Vinayakar understood. Princhi also understood. Polomi also understood. Good. Okay. So now, okay. Priya also understood. Okay. Priya is from which school? I forgot. Hello, Priya. Ankit also understood. Okay, fine. Vinayak is not saying anything.
Yes, sir.
Yes, Vinayak, are you clear? Are you clear? What I'm doing? Somehow clear.
Yes, sir. I'm clear, sir.
Okay, fine. Okay, so now let's proceed. Okay, what else to be done here? Okay, John Shika also understood. Okay, fine. So what has to be done here? Now see, what else I need to do? Okay, I need to tell you one more application which I'll take a break and I'll do. That's the last topic. Okay, I'm going to take 5-6 minutes break. Till then, what will you do? Okay, I'll give you a numerical. Okay, just check. This one is a textbook numerical. Okay, I'll just send you the solution right now only. You just check and see the steps whether it makes sense or not. This numerical is based on this is the one, okay, which I think last time somebody has asked. Okay, I remember doing it, right? For Soumitra asked me, no, this problem, this question number 14. Okay, he asked me. Yes. Okay, so yeah, I will show you this one also. Okay, let me send the question. Okay, 1 second. You check the solution by yourself. Okay, if you don't understand, you can ask me. This is one of them. I'll send you in the group. Oh no, I'll just take the photo here only right now only. Okay, then I'll send you later in the group. Please check, huh? Okay, no need to do it, just check for the time being. Yeah, both of this. I think I can take only 2 of them right now, not more than that. So both the question you check. Okay, this is what and what, right? Question number 13 and 14, huh? And you can check the solution is there only in front of you, so please check. Okay, I'm going to come back. Okay, 5 minutes break. I need my head is spinning. I'm coming back, huh? Any progress, guys? Did you understand this question? First question, just check though. Lift on the wing. Lift on the wing means what? Force, no? So it's fine. Is it fine? The question, just check.
Yes, sir.
The formulas I think is quite
Yes,
alright. The formulas I think is quite fine. Question number 13.
Yes,
Okay. Question number 14. Which one is the correct one? First one or second one?
B.
B is correct one because that's a small area there, no? So pressure will be less.
less.
So it cannot, the liquid cannot rise so much there, okay? Because the pressure is less, no? Most of the liquid is just going past, okay? Fast, no? Okay. I hope so, okay? You have understood this one. I'll just do one more topic today, that is your Venturi meter, okay? So just check. I think will not be a problem. So I'll do that. So Venturi meter I'll do from this book, right? I think fine. I'll do from here. Okay, see. So what is Venturi meter? Anybody knows what is Venturi meter? Yes. Venturi meter. Okay, you can say that it's a device. Okay, it's a device with which we can find the speed or velocity of what? Liquid in any pipe, no? Okay, in cylindrical pipe, okay, or any pipe, okay, we can use Venturi meter to do that. Okay, so try to understand this, how it works. Okay, see, guys, are you okay? What are we doing? Is it fine? It's an application of Bernoulli's theorem. Check. Okay, I'll send you the notes today only. Okay, please read today only, and then if you have any doubts again, you can ask me. Okay, next time. Okay, see, what is a Venturi meter? Okay, let me draw this diagram first. I have a pipe. Again, you can see it's placed horizontally. Okay, and it has different cross sections. Okay, one of the cross section is big and one of the cross section is small. So this is a bigger cross section. And this one is definitely the smaller cross section. Okay, I have a gap here. Let me just show you. I have a gap here. I have a gap here also. You can see I am trying to draw a gap. In this gap, okay, I'm going to keep a U-shaped tube. Okay, if you don't know the name of this U-shaped tube, it's called manometer also, no? Manometer, right? Remember this one? Anybody knows this one? Heard about this one? No. Okay, fine, let it be. Okay. Okay, let me tell you what happens here. Okay, say in this tube, okay, that I'm talking about, tube, I'm going to keep a liquid, okay, which will not be same liquid as that is flowing there. Okay, it's going to be a different liquid. It is filled right now like this. See, it's filled here like that with a different liquid. I'll write the density also of this liquid. Okay, see, and you can understand, right? We have air in between, air here. We have air here also. Okay, now think and tell me. Okay, here the pressure will be more or less pressure. More or less. Less pressure. Less push. Okay, and here the pressure will be more or less.
More, sir.
More pressure. Okay, I think you understood this one very nicely. Okay, because the liquid here can push very much, right? So the level here will be less, right? And here the level will be very high, right? Okay.
Yes, sir.
This is the difference in the level between the two levels. See, H. This is H. Are you clear what is H, guys? All of you?
Yes, sir.
Okay. So what is this H telling us? What do you think? This tells us about the pressure or pressure difference between the two cross sections there. Pressure difference. Yes. And what is the formula for pressure? Pressure is H into rho into G. Okay, but let me tell you the density of this liquid is rho m. Are you clear? And the density of this liquid which is really flowing there, no, the liquid which is flowing, I call it rho. Are you clear with the difference between rho and rho m?
Yes, sir.
Okay, so we have two different liquids, I told you, no? So the pressure formula is what? H into rho into G, but this time I'll write H rho G or H rho m now. The pressure difference will be H rho m, because pressure difference will be given by this liquid here. Can you understand? not by that liquid, okay? That will be given by this liquid. Of course, it's the pressure difference between these two levels, but it will be given by this liquid that we have here, no? So it will be given by rho m. Are you clear with this formula? And it will be giving us pressure or pressure difference. I told you just now, it will be giving us pressure difference. So the pressure on this side is P1. Let's say the pressure is how much? P2. So what's the pressure difference, guys? P1 minus P2. Okay, now let me ask you, do we know, can we calculate this H or not? Just by looking, right, and bringing a scale, can we calculate this difference or not?
Yes,
Yes,
sir.
sir.
Okay, we can calculate H. That's not difficult. Okay, we can calculate this difference in height. This G is 9.8. That's not a problem. We'll be doing on Earth, so 9.8. This rho m. Okay, I will be taking such a liquid whose density we know. Yes or no? Okay. So do you agree that easily I can find the pressure difference? Agreed with me? Just check, guys. Can I find the pressure difference very easily or not?
Yes, sir.
Okay, just come and just come and put the liquid whose density you know. Okay, so you do that. No, you put it there. Okay. Now let's go back here. See, here the area is A1. Here the area is what? Sorry, not there. Here the area is A2, and the velocity here is, let's say, V1, and the velocity is how much here? V2. Okay, so I'm going to write your equation again. Okay, that is your Bernoulli's theorem. So now you tell me. Okay, moreover, again the pressure and potential energy will be same because it's a horizontal tube, so obviously they are same level on the ground, so I don't have to write for potential energy. Okay, so tell me, what is the formula, guys? Bernoulli's theorem on both cross sections. Half, I remember half. Rho, right? I remember rho.
Rho
Velocity
is
1 squared, right?
Yeah.
Plus what?
P1.
P1. Yes, no need to write potential, right? Because it's same on both sides. They will cancel. Equal to what? Half rho
Rho V2 square.
V2 square plus
P2.
P2. Okay. Now you ask me. Okay. Now ask yourself, which one you want to calculate? You want to calculate V1 or V2? I told you we can find velocity. We can find speed of the liquid at any cross section. So I can find V1 or I can find V2. No. So let's find V1. Okay. Let's find what? V1. That means I have to come and I have to substitute for what? V2 has to be removed from this equation. Agreed, right, on this?
Yes.
Okay, because I want to calculate V1, no?
Yes,
So
sir.
I have to remove V2. How to remove V2? I'll show you. See, I can write A1 V1 is equal to what? A2 V2, and you will agree with me that it's very easy to find the cross sectional area or not? Just bring a scale, you can find the area of cross section, right? Because you can calculate the diameter, then you can apply the formula and you can get the area. Okay, so don't worry, we know what and what, guys. We know A1 and A2. We know the area here, we know the area here. That's not a problem, we can do that. Okay, so tell me, how will I substitute V2 from here? V2 is equal to how much? A1
V1 by A2.
A1 by A2, and I have to write here V1. No, this is what I'm going to use now. Okay, I'm going to use this over here. Check this V2. So the moment I do that, there will be no more V2. Okay, in this expression. No, so let me do that. Okay, so you guys have to help me out. I'm going to do it slowly. So please tell me, though, guys, what should I write? I should write half rho V1 square. Okay, then plus P1 minus P2. I can do that, right? Equals to half rho. In place of V2, what can I write, guys? A1 by A2 and V1 squared.
Square.
Okay, I'm going to arrange now. Okay, I'm going to take this, just check, I'm going to take this on the left hand side. Okay, so what will I get, guys? Tell me. Half rho is common in both of them, right? So I'm going to get what? V1 square is, even V1 is common in both of them. Can you understand? I'm talking about these two. Okay, let me do it fully only, no, not half. Okay, so let me write everything then. Okay, see, 1 second. Okay, so let me write both of them. See, what do I get, guys? Half rho V1 squared minus half rho A1 by A2 V1 whole thing square. Then I'll write here plus P1 minus P2. Then what do I write? Equals to nothing. Equals to what? 0 right now at this point. Okay, but don't worry, we know what is this pressure difference, right? Pressure difference is what? P1 minus P2, no, which is equal to how much? H rho m and what?
H rho m g.
Rho m g. Okay, so in place of this I can write H rho m and g plus, okay, this whole thing. So how to do that? Okay, check. What is common now? Tell me, guys. Half is common, rho is common,
Rho
even v1
v1 square.
square is common. So what is not common there now? 1, no?
1
From the first
minus
term,
a1 by a2.
1 minus a1 squared by a2 squared. I think we are clear with this part. Okay.
Yes.
Okay, then equals to how much?
0.
Equals to 0. Okay, now you tell me, what can I do here? See, I can write half rho v1 square. I can write here 1 minus a1 square by what? A2 squared equals to minus what? H rho m and g. Okay, now I don't want to use this minus sign. Okay, I want to remove this minus sign, so I'll take it on the left hand side, right? When I take it on the left hand side, it's going to look like this. See, half rho v1 squared a1 squared by what? A2 squared minus 1. Do you understand what I did? I've multiplied everything by minus sign, that's it. check. Multiply this everything by what sign? Minus. So this one will become plus, this one will become minus, and this one will become what? Plus, no? I think this step is clear. Check, guys.
Yes, sir.
Okay, let me just finish it now. Okay, I'm tired. Okay, you guys are also tired. Okay, so now check. Okay, so don't forget, okay, whatever we are calculating, guys, we are calculating v1, no? So I'll transfer everything on the other side. Okay, how will it look like? Tell me. On the right hand side, I'll get h, or I can get 2 also there, right? I'll get 2, I'll get h, I'll get rho m by g, not by g divided by what? Rho, right?
Rho v1 square.
Okay, v1 square will be here. Okay, and divided by what, guys? Divided by this entire thing, right? This one, a1 square by a2 square minus 1. Okay, I think you understood this step. Check, guys.
Yes, sir.
Okay, so once we get till here, I don't have to tell you much. So v1 must be equal to what? Root over of this entire thing twice h rho m g by what? Rho this entire thing. Okay, a1 square minus a2 square I can write, and then I can take here a2 square on top. No, I think you understood what I did just now. Okay, is it fine if I do like that?
Sir.
Okay, I think you understood this one.
Yes, sir. Yes, sir.
Okay, so these steps I think you don't need to worry, but you realize we have calculated what now from here? V1. Okay, how will I calculate V2? Anybody who has ideas what to do? I'll go back to your equation of continuity. Look at this. Just now I told you, right, we got which one? V1. So now I will use this, and I can also get what? Get V2. So that's not a problem. Okay, I don't think so. That's a problem. Okay, but did you really understand Venturi meter, guys? If you have understood, then I will stop. You guys can rest. I will also take rest now. Okay, can I stop, guys, for today?
Yes, sir.
Okay, so some of them, though, they have left. Okay, they got bored now, maybe in between. Okay, so I'll do this. Okay, I'll stop. I'll meet you next time. Okay, so bye. Thank you, class.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.